Welcome to BMAC.MATH tutorial. Subscribe to our channel for freshly uploaded content. This is a question from CSIR Net 2019 December, and it is a question from complex analysis from part C. We are given that f is a non-constant analytic function and x and y are two sets defined. We will check each of the conditions separately. First of all, let us write two theorems. Theorem 1. Let f and g be two continuous functions defined on a set U subset C. Then the set of points Z in U for which fz and gz agree is closed in U. And theorem 2, let f be an analytic function defined on a domain. Domain means open connected set U subset C such that the set Z in U such that fz is equals to 0 has a limit in U. Then fz is identically equals to 0 on U. We will consider the first option. We are said that x is closed in U. First of all, let us write the set x. X is the set of points Z in U such that fz is equals to 0. Now we are given that f is an analytic function, so it is continuous. 0 is a continuous function, and by theorem 1 we can say that x is closed. So 1 is true. Next, let us consider option 3. X has empty interior. Let us check the validity of the statement. Let x belongs to the interior of x. Then there exists an open ball, say B, such that x belongs to B subset x, and x is subset of U. Thus f of we should write this as z0. F of z is equals to 0 for all z in B, and we know that B has infinitely many limit points in U, and thus by theorem 2 we can say that fz is identically equals to 0 for all z in U. But this violates our condition that f is a non-constant analytic function. Thus z0 can't belong to x0, that is, there cannot be any z0 in x0, and hence x0 has to be an empty set. Thus option 3 is also correct. For options 2 and 4, let us first write y is the set of all points Z in U such that f vanishes on an open neighborhood of z in U. That is, f vanishes on an open neighborhood of z in U. Let us see if z belongs to z0 belongs to y, then by the condition of zy, f vanishes on an open neighborhood, say n, of z0 in U. Thus, since n is an open neighborhood of z0, there exists an open ball say B such that z0 belongs to B subset n, which is also a subset of U, and thus we know that B has infinitely many limit points in U, and thus by the same argument which we used in the case 3, we can say that z0, or rather fz, is identically equals to 0 on U, which contradicts the fact that f is non-constant. Thus z0 can't be in y. This is true for any arbitrary z0. Thus y has to be an empty set. And we know that empty set is both open and closed, and thus y is both open and closed in U. Thus our correct options, we have 2 and 4 are true, and finally 1, 2, 3, 4 are all correct.